Proxima Centauri b is the closest Earth-like planet we've ever found. It's right next door in cosmic terms. So why can't we go there? Why is reaching this alien world, which might even support life, completely impossible for us? The answer is a brutal lesson in physics and biology. It's a story of unimaginable distances, technological walls, and a cosmic truth we refuse to accept. This isn't just about building a faster rocket, this is about confronting the very limits of what it means to be human. Let's be clear about the distance. Proxima Centauri is 4.24 light-years away. That's 25 trillion miles. To grasp that scale, if our entire solar system was the size of a quarter, Proxima Centauri would be 2 football fields away. Our fastest human-made object, Voyager 1, moves at 17 kilometers per second. At that speed, it would take about 76,000 years to get there. Human civilization hasn't even existed that long. We're talking about a time span that dwarfs recorded history. To make the trip within a human lifetime, we would need to travel at a significant fraction of the speed of light. Think 10,000 kilometers per second. At that incredible speed, the journey would still take 130 years. That's a one-way trip longer than any human has ever lived. Our current rockets are useless for this. They're chemical propulsion systems. To reach just 1% of light speed with a traditional rocket, you would need more than 1,000 trillion kilograms of fuel for every single kilogram of spacecraft. You'd need a spaceship with 100 times the mass of Earth. The idea is laughable. It's completely unfeasible. So we must think differently. We have to abandon the dream of sending astronauts. The only realistic path is to send machines, small, automated probes. We've explored new engine ideas. Ion and plasma thrusters are more efficient. They've been used on solar system missions. The VASIMR plasma engine could cut a trip to Mars down to just 39 days, but even this advanced technology would take over 2,000 years to reach Proxima Centauri. That's not a solution. There are more radical concepts. Project Orion proposed using nuclear bombs exploded behind a spacecraft for propulsion. A giant shock-absorbing plate would push the ship forward. This terrifying idea was partially tested in the 1960s. A ship like this might make the trip in 150 years. That sounds better, but it introduces the concept of a generation ship. Multiple generations of humans would be born, live, and die inside a metal can, all to reach a destination their ancestors dreamed of. The social and psychological challenges are immense. Then there is the solar sail. This is not pushed by wind, but by the physical pressure of light from the sun. A gigantic, incredibly thin sail could slowly accelerate a probe, but for a trip to Proxima, it would still take thousands of years. The sail would have to be deployed dangerously close to the sun, enduring temperatures of thousands of degrees. The most promising idea combines a light sail with something else: lasers. This brings us to the most realistic and exciting project so far, Breakthrough Starshot. This is not just a theory, it's a real research and engineering program. The plan is revolutionary. Send a fleet of tiny probes, each no bigger than a microchip and weighing just grams. A mothership releases them into orbit, then an array of powerful lasers on Earth fires a concentrated beam of light at their sails. This laser beam would push these nanocraft to speeds of up to 20% the speed of light. That's 60,000 kilometers per second. At this staggering velocity, the probes could reach the Proxima Centauri system in just 20 to 30 years. They would not slow down. They would scream past the star and its planets in a high-speed flyby. In the few hours of their closest approach, their tiny cameras could snap pictures of Proxima b. They could analyze its atmosphere. Since the probes are so small and cheap, you sent thousands. Many would be destroyed by interstellar dust grains during the journey. But if you send enough, some will get through. They would then use a compact laser to beam the data back to Earth. That signal, traveling at light speed, would take another 4.2 years to reach us. Within this century, we could receive the first close-up images of an exoplanet. It's a breathtaking vision. But what if we ignore the speed problem? What if we could build a ship that gets us there in a reasonable time? This is where we hit a wall far more solid than any engineering challenge: the human body itself. We are biological machines perfectly calibrated for Earth. Every part of us is tuned to this planet's gravity, its 24-hour day, its atmospheric pressure, and its magnetic field. Take our bodies into deep space, and they fall apart. Astronauts on the International Space Station lose 1.5% of their bone mass every month. After a year, their bones are as fragile as an 80-year-old's, with osteoporosis. Their heart muscle shrinks, their vestibular system causes chronic nausea. And then there's cosmic radiation. Outside the protection of Earth's magnetosphere, you're bombarded by high-energy particles. A one-way trip to Mars would cause brain damage similar to early Alzheimer's in 40% of a crew. A 42-year trip to Proxima Centauri, even at 10% the speed of light, would deliver a radiation dose 300 times the lethal level. Shields thick enough to protect you would be too heavy to move. Our biological clocks also break down. In Antarctica, where the sun doesn't rise for months, people develop severe depression and hallucinations. Cosmonaut Valery Polyakov, who spent 437 days in space, described the slow slide into madness as his sleep cycle disintegrated. Now imagine this on a multi-generational ship. The first generation might be volunteers driven by a mission. Their children would be born into the metal walls of the ship. For the grandchildren, Earth is a myth. The ship is their only reality. Studies predict that by the fourth generation, most of the population would reject the mission. By the sixth generation, cults dedicated to sabotaging the ship would likely emerge. An interstellar colony must be able to reproduce, but human reproduction in space is likely impossible. In microgravity, sperm do not swim properly. Radiation damages DNA in eggs and sperm, causing high rates of sterility and mutations. Experiments with mouse embryos on the ISS showed neural and heart defects in almost every case. Gravity is a fundamental signal that tells cells how to develop. Without it, the process fails. Even if we could create artificial gravity by spinning the ship, new problems arise. The Coriolis effect from the rotation would interfere with the development of the inner ear. You would create children who are permanently nauseated and unable to balance. And what about the children born on Proxima b? Its gravity is 17% stronger than Earth's. Their bodies would adapt, their bones would be denser, but their hearts would be under constant strain. They could never visit Earth. Their cardiovascular systems would fail. They would be biological prisoners of their new world. Within just 30 generations, evolution would take over. The people on Proxima b would diverge from Earth humans. They would develop darker skin to handle different radiation, eyes adapted to the dim red light of their star. After 100 generations, they would likely be a new species entirely, Homo Proximae. They would no longer be Homo sapiens. So here's the brutal, inescapable conclusion. We can send our machines to the stars, we can send our data and our silicon chips, but we can't send humanity. Our bodies, our minds, and our very biology are chained to this planet. This is not a temporary technological limitation, it's a permanent existential constraint. Fermi's paradox asks, if the universe is so big, where is everybody? Perhaps this is the answer. Civilizations can't travel between the stars because the moment they try, they cease to be civilizations. They either die on the journey or fragment into new alien species, isolated and alone in the void. Proxima Centauri will continue to shine, a faint red dot in our sky. It's so close we can almost touch it with our telescopes, yet for creatures like us, it's forever out of reach. This is not a defeat, it's a realization. Accepting our limits might be the first true step towards cosmic maturity. Our destiny is to explore the universe with our minds and our machines, not with our fragile bodies. The universe is not ours to conquer, it's ours to understand. The challenges of reaching another world are truly cosmic. If you found the impossible barriers of space fascinating, you might be interested in the universe's most terrifying locations. For a different kind of cosmic dread, check out our video on the scariest places in the universe explained. What do you think? Should we focus on sending robotic probes, or should we keep dreaming of a way to send humans? Let us know in the comments. If you enjoyed this deep dive, make sure to like and subscribe for more. Thanks for watching.